In this video I'm going to explain the concept of an identity matrix and an inverse matrix, as well as what the determinant is. So just before we get into explaining that with matrices, it would be good to quickly recap when we're working with scalar values or just real numbers, what an identity and an inverse is. So let's start with the operation of addition with scalars or with real numbers, and we're saying the identity is a scalar which I can add onto any other scalar and it really has no effect. It leaves that first scalar unchanged. So I'm basically saying if I start with the number a and I add something onto it, I still always end up with a, and for addition that element is of course 0. And so 0 we describe as the identity for addition. For multiplication, we're saying what is the element, the scalar value or real number that I can multiply a by and it doesn't change, and that is the number 1. So 1 is the identity for multiplication. So we're going to now consider when it comes to matrices, and we're going to say, well, what is the matrix that I can multiply any matrix by and it has no change or no changing effect on the matrix that I started with. So that's how we'll define the identity matrix. So let's actually do that right now and say as a definition the identity matrix. The identity matrix is the matrix I, we don't need that comma there, the matrix I such that A times I equals A, and other way around is true as well, I times A equals A. Maybe I'll put a little, let's put an and in there, and I times A equals A, and obviously we mean here for non-zero A. So if A was all zeros, then the definition wouldn't hold here because I could be really anything there. So we're saying for a non-zero A, in other words a matrix A which is not all zeros, the identity matrix is the one such that A times I is equal to A. It leaves it unchanged. Now, in practice or in appearance, that means that the identity matrix is one which has ones down its leading diagonal and zeros elsewhere. Let's actually say an identity matrix because obviously depending on the size of the matrix, it will be a different size. So an identity matrix has all ones on the leading diagonal and zeros everywhere else. So let's go a couple of examples. So for a 2 by 2 or an order 2 matrix, I would be equal to 1, 0, 0, 1. So the leading diagonal is the one which goes down from the top left corner to the bottom right corner. If we were talking 3 by 3, we would have the identity matrix starting with a 1 there, zeros here, a 1 there, and then a 1 down there. So again, all ones on the leading diagonal and all zeros everywhere else. And we could, keep it sort of expanding that up to matrices of larger order as well. Alright, so that's the identity matrix. And what we'd find is that any other matrix of order 2 that we multiplied by that, or multiplied that by, would remain unchanged. Now let's consider what the inverse of a matrix is. And again, if we just for a moment consider the inverse of a scalar value, that is the thing that I can, well, if we're talking about addition, it's the thing that I can add on to A such that I get the identity. which for addition is 0. For multiplication, it's the thing that I multiply by A, such that I get the identity, which is 1. So for addition, the additive identity is just the negative of the value we start with, isn't it? So A plus the negative of A. And for multiplication, it's 1 over A. So straight away that means that 0 doesn't have an inverse for multiplication, does it? Because 1 over 0 is not defined. But every other scalar value has an inverse for multiplication, and every scalar value has an inverse for addition. So we're going to define that the same way for matrices, and say for matrices the inverse, so the inverse of a matrix A, we should say if it exists, because it won't always, is, and we use the notation a to the power of negative 1. We don't mean a to the power of negative 1, it's just a notation for A inverse, such that A times A inverse equals I, and we could also say A inverse times A is equal to I. So that's how the inverse of a matrix is defined. It's the matrix that we multiply by any matrix to get the identity. Now, if it exists, then we say that A is invertible. So if A inverse exists, then we say A is invertible. So it's possible to find its inverse, or non-singular. Okay, so invertible and non-singular here have the same meaning. Now, most of our work at the moment, in fact pretty much all of our work at the moment, will be with 2 by 2 matrices. So let's just consider for a moment specifically for a 2 by 2 matrix, and we'll just use the sort of general definition or notation we use for a 2 by 2 matrix. So with elements A, B, C, and D, A inverse is going to be, we can calculate in this way here. Whoops. D, it's not very neat. Let's go D, A, negative B, negative C. Alright, so with a 2 by 2 matrix, there's a nice little algorithm or result that we can use to find its inverse if it exists, and it will be 1 over the product of AD minus the product of BC, and then the matrix, we swap the entries in positions A and D, and we reverse the sign on the entries in positions B and C. Now from that we should be able to see that the only time that an inverse won't exist is when this value here is 0, because then we'll be doing 1 divided by 0. So that value there is actually called the determinant, because it determines whether a matrix has an inverse or not. So the value AD minus BC is called the determinant. And so some notation for that, so we could say that det A equals AD minus BC, or sometimes we use the sort of absolute value notation for determinants, so you need to be familiar with that as well. The determinant of A equals AD minus BC. Now, if det A equals 0, then it doesn't have an inverse, so then we say A is singular. So when a matrix doesn't have an inverse, we say it's singular. It kind of appears by itself. Alternatively, we could say it's not or non-invertible. Okay, that would be another way of saying singular. So let's just quickly do an example here. So let's define a matrix, -2, 5, -3, 7, and B can be the matrix 10, 5, 4, 2. So then we could say that A inverse is going to be 1 over the product of A times D, that would be -14, minus product of B times C would be -15. We're going to swap A and D around. Negative of this one and the negative of -3, which is +3. So that's going to be 1 over 1, isn't it? So the determinant is equal to 1 here, which makes this one nice and neat. And obviously a lot of the time they're not that neat. So that's A inverse. And if we were trying to calculate B inverse, we'd be saying 1 over 10 times 2 is 20 minus 20. And so in fact we would say it doesn't really matter what's in there. So 2, 10, -5, -4. So B inverse does not exist, as det B is equal to 0. So if the determinant's 0, it is non-invertible. It's a singular matrix. It doesn't have an inverse.